Fluorescence is a phenomenon that underlies a lot of things in biomedical optics. Let's think of it as the simplest diatomic molecule that we can, which would have two nuclei here, and some amount of shared electronic structure, which I'm going to write for simplicity as just some sort of distribution shaped around here. We don't have to be too rigorous about it. And I'm going to call that S0 for a singlet state. We don't need to care about why it's called a singlet state, but it's an electron distribution shared amongst these two nuclei. And now we can start to talk about the energy structure of this diatomic molecule, which is a stand-in for any molecule which might have more atoms than that. So there's a separation between these two nuclei. We could think of it as the bond length that anchors these two nuclei. And there's some representative distance. I'm going to call it R0, R0. And that's the sort of equilibrium distance between these two nuclei. They're not static relative to each other, as we'll discuss when we start talking about vibration. But let's call R0 the equilibrium distance between the two nuclei. So we could start making a plot of this radial separation and talk about the potential energy in this molecule as a function of that separation. So let me draw some axes here. So on the x-axis, we're talking about the nuclear separation. And on this x-axis, I can make some mark here corresponding to R0. Now, if I bring these nuclei closer together than R0, the electron cloud doesn't screen them from these two positive charges seeing each other's charge quite as much. So you start to get repulsion. One of the reasons why you can't press these nuclei while they don't want to get closer together than R0 is they see more and more of each other's charge and it's repulsive. There's some value here of the potential energy. So as you move towards smaller values of separation, you see nuclear repulsion taking that curve upwards like that. I didn't mean for it to hit the axis at R0, but that's sort of where it goes. Blows up at infinity, can't get the two nuclei too close to each other. In the other direction, if we try to pull these nuclei farther apart from each other than their equilibrium separation, there are attractive forces that pull them back. We're not trying to appeal to the physics of that right here. We're all comfortable with the idea that there's some equilibrium bond length, and if you try to go beyond that, the system tends to want to return back to this equilibrium value. And what this does in practice is it sort of flattens out, and there's a bowl, and if you stretch it far enough apart, you can rip it apart. But we're going to live inside of this bowl here so that we don't really care about the details too far away from the bowl. So again, this is the potential energy of this arrangement as a function of how far apart the nuclei are. Now, the first step in the fluorescence process is that the molecule absorbs a photon. Now, what does it actually mean when we say that a molecule absorbs a photon? It means, for a visible wavelength photon, that it goes up to a higher electronic energy state. We're all used to electronic energy states. We learned in our chemistry classes about s orbitals and p orbitals, the idea that electrons can have more or less energy. If this little diatomic molecule absorbs a photon, we can represent that by suggesting that the electron distribution gets more spread out and spends more of its time, or more of the electron charge density, is spread farther away from the center of this system, sort of the origin, where I've made a little dot here. So we have an electronic excitation state here. And now that the two nuclei are not going to be screened from each other as much, there's not as much negative charge in this region in the middle. So there's a repulsion that happens. And if we sort of just drop this separation here down and preserve that R0 separation, there's, for this S1 state, this excited singlet state, the new equilibrium separation between these two nuclei, the one on the left and the one on the right, maybe we write this now as their new equilibrium separation, and this distance here, R1, which is clearly greater than R0, I'll draw in over there. So I could make another mark on this axis here of nuclear separation and say that's the equilibrium separation when the molecule is in its excited electronic state. So since the excited electronic state of this molecule is going to have its equilibrium position at a different R1, we have to draw a bowl like this, but we have to draw it at some different starting value. So we're going to draw that is the bottom of the S1 energy state as a function of nuclear separation. I'll just draw the bowl part. We don't need to draw the rest of it. So here's the bowl there. So this is the S0 state here, and this is the S1's shape up here. So this is the electronic structure. Now, the important thing is that we have two atoms, not just one, and since we have multiple nuclei, they can also vibrate. If you imagine that what these nuclei are two nuclei with a sort of spring in between them. Now we have two masses attached by a spring, which is of course the chemical bond, and so there's a vibration. Each nucleus moves to the left and right, and you can imagine the distance between them getting bigger and smaller. And that's what this bowl here does represent. If we draw some energy levels in here, you may be familiar with having seen these from classes, depending on what you've taken. And we can also fill in some energy levels here. So just as we're comfortable with the idea that electronic distributions, like s orbitals, p orbitals, and so on, have different quantized amount of energy, similarly to electronic states having quantum jumps between them, it's true for vibrations as well. So what these lines here represent are the different amounts of vibrational quanta that can exist because the two nuclei can vibrate. And these are vibrational quantum levels. And it turns out empirically that the spacing between these quantum vibration levels is about 1/10 as much energy as the jump between electronic levels. That's a rough order of magnitude, about a factor of 10. Now that we've got this basic energy diagram set up over here, let me make an assertion now. When a photon is absorbed, causing this molecule to go from its ground state of both electronic and vibrational energy up to an excited state, the assertion that gets made is that it goes, basically, we're just going to pretend it goes straight from the bottom here, not going to actually put it on that red line, and we go straight up, and we hit here. So the assertion is that we start off with a state A. It's in the lowest vibrational energy state, which will index 0. And the assertion is that we're going to end up in this particular diagram in what would be a state we'll name B, and that has 2, that's indexed level vibration 2. So let's defend that statement, because this is really the point of this tutorial, is to understand why we would draw the energy diagram that way and what reasoning we can extract from it. So let's draw an arrow over to here and talk about what that motion kind of looks like. Well, I'm going to draw two atoms. I'll give you an atom here and another atom here. The meaning of a diagram like this is that it's a very low energy vibration, very low amplitude. This bowl basically tells you how large an amplitude of oscillation is happening, and at the bottom of the bowl there's almost no amplitude. So I can cartoonishly say, I'll draw two little arrows here saying that there's a small amount of amplitude oscillating back and forth for these two nuclei, but in the limit we can think of them as basically stationary. So that might represent the motion of these two nuclei when they're in their lowest vibrational state. Now the assertion is that when a photon of energy is absorbed, it somehow goes straight up to here, and notice something about point B. It has the same internuclear separation as the initial state did. So we have to draw the two nuclei as being at the same separation apart the instant after the photon is absorbed as the instant before the photon was absorbed. So we will draw here the interpretation of this vibrational state is that we also have the same separation, but look at what the motion diagram tells us is happening for the state B. So the separation is at smallest is as drawn here. There's the smallest separation between the two nuclei, but they can get much farther apart, which on this graph means that they go to a larger separation. So what we've got here, on the bottom, we've got the initial vibrational state. And then at the end, here's the final state. And the assertion being made here is that the nuclei, drawn before and after, the nuclei change neither position nor momentum, or speed. In this case, it's equivalent to say that, on this time scale. What do I mean by time scale? I mean the time it takes to go from the initial state up to the final state. And that time is on the time scale of one oscillation of the electric field. So we can, for the moment, let me just say that maybe we're absorbing a visible photon at 500 nanometers. Let's not figure out what the optical frequency of that is. Let's just hold in our minds that this might correspond to the absorption of a 500 nanometer photon, and therefore the time period of oscillation of a 500 nanometer oscillation. Vibrational states, it turns out, if you were to absorb a photon that instead of increasing you up to a higher electronic state, it just kicks you up one vibrational level, it turns out that that corresponds to a lambda of a reasonable number, a representative number, turns out to be 5,000 nanometers, not 500. So it's not a horrible approximation to say that on the time scale it takes to make this optical transition corresponding to a 500 nanometer photon, the nuclei don't have time to move very much. The electrons redistribute themselves on a time scale much faster than the much heavier nuclei do. And in terms of time scale, the time it takes to make this sort of transition is usually associated with something like single femtoseconds. So this should remind you of stuff you learned in physics, that when you apply a change, a force or something to a system of masses, you can't instantaneously change their position. That would require an infinite force. And you also can't instantaneously change their velocity. That would also require an infinite force. So that's really all that's being asserted here, is that on the time scale that the electron gets absorbed, the nuclei have time neither to move nor to change speed. And that has a name. I'll just write it down for you here. It's the Franck-Condon principle, if you ever need to look that up, and of course it's in our book as well. So that's the assertion there. Or it's part of that assertion, to be more precise. Okay, that was actually the hard part. Now what we have to think about is when this is just depicting the absorption event, what happens when there's a fluorescence emission taking us from the upper state down to the lower state? So the important thing that it gets asserted here is that the bowl corresponding to the S0 state and the bowl here corresponding to the S1 state, they look the same except for the shift sideways and the shift upward, of course. But aside from this sideways shift, the bond strength stays about the same. It's just that the internuclear separation equilibrium changes a little bit. And that means that we're basically saying these two overlap each other very closely, that the level structure in both of them is essentially the same. The next thing that happens, you will have to trust me on this, is that once the molecule finds itself in state B, it very rapidly relaxes non-radiatively down to a state at the bottom of this bowl. I'm going to call that state C. That's where the similarity of these shapes comes in. We make the assertion that if the most likely absorption connection starting from location A, if that we wrote out as being in the ground state of, in other words, S0, and in the 0th vibrational level, that's state A. If the most likely thing to happen there is for us to go to the excited electronic state, call that E, and the number 2 vibrational level, in other words, that's going from A to B, then the most likely emission event, that's what we're going to call our fluorescent photon, is the reverse. That we would, you notice that state C, we could write here as being in the excited electronic state, but in level 0 vibrationally. The most probable thing that's going to happen from there turns out to be that we'll go to a state D, which is right here, straight down, and that, by the symmetry of these two shapes being the same, by shifting over sideways, if A takes me up to B, hitting the second level up vibrationally, then going from C down to D, that's going to land me in the ground state and in the second level vibrationally. That's the key assertion that's happening here. Up and down follow those same absolutely vertical jumps. So if I now write out a time sequence for what's happening, what we've got is that we start off in state A, an absorption event happens that takes us up to state B, and that's on a femtosecond time scale. Then there's some relaxation of this upper state here, which takes us to a state C. And that time scale there, think femtosecond or picosecond time scale to get from B to C at most. And I want to point out that there's energy loss occurring in this step here. Energy is lost to the environment. This relaxation here is carried away as thermal energy shared with the system. Then I'm going to write a little gap here to say a fairly large amount of time can elapse before eventually state C would radiate an emitted photon and the molecule returns to level D. And it's very important to know that this is a much longer time scale. So that's a nanosecond time scale there. And then D, just like B decays to state C, D can get thermal interactions with the environment and then quickly relax down to state A. That again happens on the same femtosecond scale as B relaxing to C. You got D relaxing to A. And when D relaxes down to A, there's again energy loss. So that's the time sequence that's happening here. There's only a few last things to know. One is that when I've drawn this squiggly thing here, there's a big question that hasn't been answered yet, which is how likely is it that when we're in state C, that what will happen is that there's an emitted photon which carries away the energy that we can then detect and call it fluorescence. We don't have space to talk about that a lot here. We're going to discuss it, but I want to let you know what the term is. That's called the quantum yield, and it's the ratio of two rate constants. It's the rate at which, if this system is only allowed to dissipate the energy from C by fluorescence, there's a certain rate associated with that. How quickly would the decay happen on average? And we could call that a rate constant with units of rate or inverse time, and we could call that K. That's often the value we use, the letter we use for rates, and that would be called K fluorescent. However, we could also say, suppose there was no possibility of it radiating a photon away. Suppose the only way that it get from C to a lower energy state is to have a collision with its environment so that it loses its energy and eventually ends up back at A, the bottom of the barrel. That we could call another rate constant, and we could call it K non-radiative, NR. These are the two things that can happen. Either it fluoresces radiatively or it gets rid of the energy non-radiatively. And if we just take the sum of those two rates and look at how Kf compares to the sum of those two, that's defined to be a quantity which we call phi, and that's what we call the quantum yield. So this is obviously a quantity that can range from 0 to 1. It's 1 when the non-radiative term is negligible, and almost all times that you're in C, you fluoresce down to D. And in the opposite extreme, where the non-radiative pathway is the strongest one, the K there is very large, and this value goes to about 0. So, final takeaways from this tutorial. The first thing is that notice that the energy of the fluorescent photon is less than the energy of the excitation photon. So we would say that the fluorescent photon has less energy. That's a standard thing, that whatever wavelength you excite with, you almost always, and certainly in biomedical optics, it's almost universally true, that the emitted photon has less energy. That has a name that you might want to know. That's named after someone, and it's called a Stokes shift, or a red shift of the photon. The second thing to keep an eye on is that while the molecule is not in state A, once it's participating in this cycle, and especially while you're waiting for it to get out of state C, which is the rate limiting step, getting out of state C, this molecule can't absorb another photon from state A. So the process of doing this, it requires on the scale of nanoseconds to complete a cycle. So as we study the temporal dynamics in class of fluorescent decays, you should also be aware that you can't excite another fluorescence photon to be emitted from this molecule until it's done processing the energy from the first one. At least in this simple two-level model, there's nothing else it could do. And that's a concept that we need to hang on to as well. There's one last thing I'll tease you with, and that's to draw an arrow to this state in here and ask, how likely, when a photon is heading in, about to interact with this molecule, how likely is it that the molecule will be in its ground state? We will discuss that in class as well, but the answer is that it is extremely likely that it will be in its lowest electronic state, and quite likely that it will be in its lowest vibrational state. So I'm going to put a little check mark here to say it's a pretty good approximation for interpreting experiments to pretend that the molecule was just in its bottom state.